Team, second class. All right, we're talking about conservation of linear momentum. It's an important part of the WPR. So let's start off with talking about conservation of linear momentum, talking a little bit about its concepts. Thanks to Tim Rossman that wanted me to talk about concepts, and I completely understand them. So conservation of linear momentum, let's start off understanding what conservation of momentum even is, or what is even momentum. So momentum is equal to mass times velocity. Now notice that I put in here a vector, meaning that thanks to momentum, we can actually identify where exactly is an object going at what direction. And it helps us especially when it comes to collisions. In collisions, if two objects smack each other, right? This is initially. It would be extremely beneficial to find out, in many instances, after that collision, where exactly, what direction is that object going at? And that here, that vector velocity is what helps us identify that. Now, keep in mind, velocity in terms of the conservation of energy, in terms of energy, it is not about a direction-based velocity. It is path independent for conservation of energy. Okay? So for conservation of momentum, vector velocities is extremely important. For conservation of energy, it is not. And we will show you an example, okay, later on. So we have identified what exactly is momentum. So momentum is just describing the motion of an object and the direction of that object. It helps us identify, especially after a collision, like where is that object going after a collision happens. So that's why we use momentum. Now, conservation of linear momentum helps us describe even further that collision-based momentum. So we have to understand two things about conservation of energy, or conservation of linear momentum. Scratch the conservation of energy part, that was the confusion. Conservation of linear momentum, we have to understand that it is a closed system. So a closed system means that regardless of the impact of two objects, let's say that these two objects have impacted, their mass, each of their mass is going to stay constant. It's not going to change because of that impact, okay? No parts are going to fly out. For example, if there's a car crash, there's the likelihood that the car is going to lose some of its mass because its windshield's broke and it flew apart, or something else just flew out of the window, and it loses mass. So that in itself wouldn't be a conservation of linear momentum because it is not, the mass doesn't stay constant. So we are assuming here that there is that collision, the mass will stay constant in that collision, okay, for both objects. Then we have isolated system. So an isolated system simply means that there is no external forces acting on your system. So that's why it's called an isolated system. These are the only two systems at play at that moment. There's nothing else, no external forces that are entering that cannot cancel out. That's why we have the sum of all external forces is equal to 0. It doesn't mean that there is no external forces acting on the system. It just means that those external forces are just going to cancel out due to the famous Newton's third law. For every action, let me erase this. For every action, there is an equal and opposite reaction. That's why there is a sum of all external forces is 0, because it is applying that. For every action, there's an equal and opposite reaction, and because of that opposite reaction, those external forces cancel out. Okay? Now, that we understand conservation of linear momentum, what it means, you have to understand also that what we are talking about conservation of linear momentum, the reason why we can conserve it is because we don't care what happens in between that. Let's say, like, let's talk about now collisions. We don't care what happens in between that collision. What we care what happens is initially, like right before that collision, right before they actually hit, and after, let me write initial, and then after, right after that collision, it's like that's what we care about. That split second before and that split second after. Okay, that is that collision. It is different with impulse, and I'm only bringing impulse just so you can understand. Impulse is equal to this, and let me J. Impulse is equal to force, average force, times change in time. So impulse is different, and it can be written as change in momentum, because in impulse, we actually care about like what happens in between that collision. So in conservation of linear momentum, we only care about what happens before and after. And impulse, we actually care about like, okay, so once that impacts, how long did, like that timing that they were together in that impact, what was the force, and what, like, how much time did they stick together for us to solve what was the impulse of that object. Okay, so that is the main difference between conservation of linear momentum and using those equations and impulse. Okay, let me erase this because this is a side note, and you know how much I love side notes. Okay, so now we're talking about collisions, and we're talking about what we care about, the before and after. So now that we are in collisions, let's talk about the famous elastic collision. Elastic collision. Everything that we talked about, it has to be a closed system. Actually, let's just put it as it has to have conservation of momentum. Conservation of momentum, which applies with closed system and isolated system. It also needs to have conservation of energy, meaning that the famous equation, the work due to non-conservative forces equals final mechanical energy minus initial mechanical energy. This work due to non-conservative forces is 0. So it means that all the information, all the energy that was experienced in this system that wasn't transferred to something that we could not use, like friction or thermal energy, or like just like the deformation of the object where you lose energy as well. It is just like an impact where none of that energy was lost due to that impact. A great example, let's talk about a little bit of an example. A great example is the famous ones that I've been doing, where you have two objects ramming each other, about to ram each other initially, and then immediately after that collision, they separate, taking their separate ways on opposite ends. There is always an elastic collision. It comes to elastic collision, there's always like a separation after the impact. Okay, they do not stick together. They just completely divert into different directions. Okay, they never stick. That is the main most important thing about, well, a key factor in understanding what elastic collision is. Okay, so we understand this, but also remember that I talked to you about that conservation of momentum is, in fact, a directional factor. So we have to address an y and x component. So we have a coordinate axis. In this case, there's only motion in the x direction. But immediately we can identify that when it comes to the sum of all momentum initial and the sum of all momentum the final, since this is a conservation of linear momentum, anything that happens initially, all the momentum that happens initially is going to equal to all the momentum that happens at the end. So initially, looking at our graphs and looking at the x direction, because that is the only direction that is happening, I'm going to write down here, let me just write down here x and x. So initially we have mass times velocity, and I'm going to identify this as mass 1 and mass 2. Mass 1 and mass 2. Mass 1 times velocity initial is going to be positive because it's going in the positive x direction. Notice, positive x direction thanks to my coordinate axis. Okay, so it's going in my positive x direction. Meanwhile, my velocity for block 2, for mass 2, is negative because it's going against the positive x direction. So we have mass 2, velocity 2. Okay, that, as I said before, the sum of all initial momentum is equal to the sum of all final momentum. So that would equal to whatever I have here. And this right now, since mass 1 is now on the other side, is going opposite of the direction of motion, I'm going to write down negative 1 mass times velocity final plus mass 2 velocity 2 final. Notice, because now it is going in this direction, it is positive. Now I can solve for any of these, whatever they are asking me for, and we're going to do a problem pretty soon, whatever they're asking me for. And if they ask me for velocity, and this should be initial. If they're asking me to solve for velocity final, I can. If they're asking me to solve for velocity initial for 2, I can, because I have set up my equation. You can also prove that this is an elastic collision by using what I told you before, that mechanical energy, conservation of energy, the final mechanical energies minus the initial mechanical energy is equal to 0. So we can use the same components. It's like, instead of looking at these blocks in momentum, we can identify them as kinetic translational energy. Okay, so let's write kinetic translational energy for 1, which is the first block, and kinetic translational energy 2. Initially, we have 1/2 mass 1, velocity 1, initial, squared. Okay, using the mass and the velocity, the initial velocity of that first mass. Okay, and then we have, and I forgot, this is mass, the final. This is mass 1, but this is actually final. I always do that. Final. And the same goes for kinetic translational, which is final here too, for 2. And then I go about the same way for the initial aspects of that block. So all you have to do now is identify, you sum up the final, and you sum up the initial. And if these two, once you sum it up and then subtract them with this equation, equals 0, then this is an elastic collision. Okay? This is an elastic collision. Whew. All right, let me add a page here. Add page, here we go. To talk a little bit more about Okay, so now we talked about like what's so important about elastic collision. It's this part right here. It is understanding that conservation of energy is involved in this one. So like work due to non-conservative forces has to be zero in order to be an elastic collision. Usually in a problem in a WPR, they'll probably give you something to the effect like, hey, it's an elastic collision or an elastic collision, but just in case, for future reference, like, hey, prove to me that this is an elastic collision, this is the way to do it. It's like identifying, instead of seeing this as momentum, now identify them as kinetic energies or potential energy, whatever. Well, it usually will be kinetic energies because they will be moving, okay? So the difference when it comes to inelastic collision is not necessarily there's been a lot of references, they stick together and that's how you know that it's an inelastic collision. I used to think that too, but over time I learned better, and it's not really about that. It's about that even though there is conservation of momentum, there is no conservation of energy. So the same example that we talked about here for conservation or the elastic collision could also apply, the same form could also apply for inelastic collision. The main difference is that once you do the analysis for conservation of energy, and you find out that you're finding out the final and the initial mechanical energies do not equal zero, it means that there is some work due to non-conservative forces, and because there is some work due to non-conservative forces, there is inelastic collision. That is the main difference. That they stick in elastic collision, they do stick together from time to time, absolutely. Initial, boom, and then all of a sudden they're together, and that is the final. But if you do the analysis, the actual analysis for conservation of energy, you'll find out that like with these collisions, when they stick together, yes, there will be a loss of energy because they are sticking together. All right, and that is also called, when they stick together, it's called a perfectly inelastic collision. All right, almost done with this lesson. So it's a little bit long, I admit. But let's talk about a problem. This is actually a problem from a previous WPR that was given, and I thought that would be essential for you just to see like how it is. So in this situation, they're asking, even though it's not listed here, they're basically asking to find out the velocity, the final velocity of this system, and you need to find out the magnitude and direction. Okay? You are given, I'll give you 10 seconds to read the problem. You are given, let's see, you have velocity 1, and you have velocity 2 as a vector. You have mass 1, and you have mass 2. Okay? So those are the only things that were given to you. The first thing when it comes to this, when you identify this as a conservation of linear momentum, the first thing that you should do is physics. Oh, I know this. It is the sum of all initial momentum is equal to the sum of all final momentum. Okay? And momentum is equal to mass times velocity vector. Okay? This will definitely help you out. Make sure that, if nothing else, make sure that you write these equations out. Equations identifying the actual physics of the problem is extremely important for us. It's like even though you don't know anything else algebraically, at least you can identify, oh, this is a conservation of linear momentum equation or a problem. This is what it is, and we will credit you for that because at least you have an understanding of what we're trying to seek. Okay, so we identify that, and now let's identify the directions. So it's giving us a coordinate axis, x and y. That means they have different directions. It means that we have to find the momentum in different directions and in the x and y component. Remember, when you're given different directions, it means that we have to break up the momentum between x and y. It's extremely important, and it's just not one direction. So let's start out with understanding. Let's break it out with the breakup of the x component. So first, we see that, hey, they're about to collide, then they collide, and it's giving us a vector. Like, we have to identify the final velocity. So initial equals final for x direction. For the x direction, if we're looking at this correctly, mass 1, and let me close this up. So the only component working in the x direction at this moment is mass 1. So mass 1, velocity 1. Mass 2 is completely vertical. So that means that mass 2, if we were to write it like in an actual component, let's put it in an angle notation. Cosine, since we're dealing in the x direction, cosine of 0 because it doesn't have any incline, plus mass 1 or mass 2, velocity 2, cosine of 90. Because we're looking at it in the x direction, cosine. Okay, so angle here is 90, angle here is 0. So that means that cosine of 90 is 0, so this cancels out completely. And then cosine of 0 is 1. So what we have is, for the only thing that's working for the momentum in the x direction is mass 1, velocity 1. That equals to mass 1 plus mass 2, because now they're sticking together. You see here, mass 1 plus mass 2, they're sticking together after the collision. And they have a certain velocity, but we're finding, since we're only dealing in the x direction, we're finding the velocity in the x direction. So look at it in this perspective. We are finding the velocity in the x direction here, velocity final x direction. And the next component is going to be velocity final in the y direction. And once we have these two components, we can use the Pythagorean theorem and find the magnitude of that velocity. Okay? So we have mass 1, velocity 1, over mass 1 plus mass 2, velocity final x. Now, keep in mind that mass 1 is positive because it's going in the positive x direction, and mass 2 was also positive in this one because it's going in the positive y direction. Okay? That's why they were positive. Now, if we have done this, too easy. This is too easy problem. Now let's go to the momentum in the y direction, the sum of momentum in the y direction. Again, we do the same things. Let's do the analysis. So let's write it down. Mass 1, velocity 1, sine of 0, because we are looking at it with the angle. Sine of 0, there's no angle in it, plus mass 2, velocity 2, sine of 90. It is completely vertical. So like this is where you see I'm just doing that trigonometrically so you can understand why these things cancel out. But sine of 0 is 0, so that means that there's no momentum in the x direction, but there is definitely momentum in the y direction, and this is sine of 90 is 1. Now that we identify that, we go as mass 1 plus mass 2, velocity final, y. Again, it's because they're sticking together, and now that they stick together, they have only one velocity together, okay? But now we're finding velocity y final right here, okay? So we do the same thing, mass 2, velocity 2 over m1 plus m2 is equal to velocity final y. Done. So now you have the vector notation for velocity final. The final velocity is equal to final velocity x, final velocity y. Boom. I've identified it as a vector notation. This is vector notation, but we want the magnitude. So since we want the magnitude, just do the Pythagorean theorem. And you should get the vector, or not the vector, but the magnitude. If you want the angle, this is where you do the trigonometric functions and just find arc tangent of velocity y final over velocity x final x, and that should give you the angle that we're trying to identify right here. Okay, so we have found the problem that we have identified this as a completely inelastic collision. And that means also that if we do the analysis where we're trying, let's do like a little example, like let's do the analysis of work due to non-conservative forces is equal to final minus initial, just so you know what to put. So initially, we don't care, as I said before, we do not care when it comes to conservation of energy what direction is this. We do know that there is a velocity, so we can write down mass times velocity 1 squared, mass 1 over 2. We're trying to find now the kinetic energy of mass 1, and we use the information. We have the mass. We have the mass of the block, and we also have the velocity of that. I say block, but it's a particle. You know how physicists are. We use random objects just to try to explain to you physics instead of using actual objects. Okay, me griping. And again, I completely missed it. We're talking about the initial. So initially, 1/2 mass 1, velocity 1 squared. We do not care about the direction. And then for the other object, 1/2 mass 2, velocity 2 squared. So we have identified the mechanical energy at the very beginning, but we have to identify the mechanical energy at the final, because now there is just one system, because we are considering mass 1 plus mass 2 being together, and it forms one system. We now only identify mass 1 plus mass 2, velocity final squared. Notice that this is just one system now. One system, because they are together. Okay? You sum these up. Due to non-conservative forces, mass 1 plus mass 2, final velocity squared, minus 1/2 mass 1 velocity 1 plus 1/2 mass 2 velocity 2 squared, and the summation or the subtraction of these two components of the final mechanical energy minus the initial mechanical energy should not give you 0. It should give you some value that says that due to that collision and due to them sticking together, there was some loss of energy as they collided, as they're sticking together now. Okay? So this is conservation of linear momentum. Pay close attention to this problem. It will definitely help you out. I want you to focus on that. I'm going to keep it here for a second just so you can, grab it with your cut and paste. Pay close attention to this problem. It will help you out. And I hope this whole lesson was helpful. It's pretty long, but I'm sure, preparing for your WPR, just, look at this one, okay? Anyway, that's my second lesson, and I'll hit you back with the conservation of angular momentum.